Welcome to this coding problem walkthrough. Today, we're tackling LeetCode problem number 1418, display table of food orders in a restaurant. This is an interesting problem that challenges your ability to organize and manipulate data efficiently. Let's dive in and break it down step by step. In this problem, we are tasked with creating a structured summary of food orders in a restaurant. Each order is represented as a list containing three elements: the name of the customer, the table number, and the food item ordered. Our goal is to generate a display table that organizes this data in a specific format. The first row, known as the header row, begins with the word table and is followed by the names of all food items sorted in lexicographical order. The subsequent rows correspond to individual table numbers, listed in numerical order. Each row starts with the table number and is followed by the count of each food item ordered at that table, aligned with the order of the food items in the header row. The result should be returned as a 2D list of strings, which will serve as the finalized display table for the restaurant. The output of this problem is a 2D list of strings representing the structured display table. Let's consider an example to understand this better. Suppose the input orders include multiple customers across different tables, each placing orders for various food items. For instance, David orders ceviche and fried chicken at table 3, while Carla places an order for ceviche and water at table 5. Corina, sitting at table 10, orders a beef burrito. The output must start with a header row listing the table followed by the food items sorted alphabetically: beef burrito, ceviche, fried chicken, and water. For each table, the corresponding row will show the table number followed by the count of each food item listed in the header. For example, table 3 ordered 2 ceviche and 1 fried chicken, so its row will be 3, 0, 2, 1, 0. Similarly, rows for tables 5 and 10 are added based on their respective orders. Breaking this example down further, the first row of the output, the header row, includes all food items sorted alphabetically: beef burrito, ceviche, fried chicken, and water. For table 3, the row reflects 2 orders of ceviche, 1 order of fried chicken, and 0 orders of the other items. Table 5 shows 1 order each of ceviche and water, while table 10 includes 1 order of beef burrito. Each table's data is represented in numerical order, and the counts for each food item align with the headers. This ensures that the display table provides a clear and structured summary of the orders placed across all tables in the restaurant. Now, let's analyze another example. Consider a scenario where all orders are concentrated on just 2 tables, table 1 and table 12. For table 12, multiple customers order fried chicken, resulting in a total of 3 orders. Table 1, on the other hand, has 2 orders of Canadian waffles and no other items. The header row for this example includes Canadian waffles and fried chicken, sorted lexicographically. The output rows for the tables will show the count of these items in the same order as the header. Specifically, the row for table 1 will be 1, 2, 0, and the row for table 12 will be 12, 0, 3. This demonstrates how the display table adjusts to the specific set of food items and table numbers present in the orders. Finally, let's look at a simpler case where all orders are placed at a single table. For instance, table 2 receives 1 order each for bean burrito, beef burrito, and soda. The header row in this case will list these items in lexicographical order: bean burrito, beef burrito, and soda. Since there's only one table, the second row in the output will represent table 2 with the counts of each item listed in the same order as the header. That row will read 2, 1, 1, 1. This example highlights how the solution handles minimal input while maintaining the required format. The constraints of the problem ensure we account for up to 500 orders, distinct food items, and proper sorting of table numbers. Edge cases such as single table or single item scenarios are addressed naturally by the structure of the solution. To start, let's consider the brute force approach. The intuition behind this method is fairly straightforward. We process the orders list step by step, manually counting the food items for each table. This involves using a nested loop to iterate through the orders and construct the display table one element at a time. Specifically, we would parse the orders list and use a data structure, such as a dictionary, to store the count of each food item per table. Once all the data is collected, we manually sort the table numbers and food items and build the result accordingly. However, this method is inefficient. The time complexity is O(n)² due to the nested iterations required to process and organize the data, and the space complexity is O, n plus m, where n is the number of orders and m is the number of unique food items. These inefficiencies, coupled with the sorting overhead, make this approach unsuitable for larger inputs, such as when the number of orders exceeds 10,000. It is clear that this method struggles to scale effectively. Now, let's move on to a more efficient solution, the optimized approach using hash maps with sorting. The key intuition here is to divide the problem into two main parts: first, counting the orders efficiently, and second, formatting the display table based on those counts. To achieve this, we use a dictionary of dictionaries, where each table is associated with a subdictionary that keeps track of its food item counts. By parsing the orders list, we can populate this hash map efficiently. Once the data is organized, we extract the unique food items, sort them lexicographically to define the column order, and separately sort the table numbers numerically. With the sorted food items and table numbers, we can construct the display table by referencing the counts stored in the hash map. This approach significantly improves efficiency, with a time complexity of O, n plus m log m plus k log k, where n is the number of orders, m is the number of unique food items, and k is the number of tables. The space complexity is O, n plus m plus k, which accounts for storing the counts and the unique items. This method not only handles large inputs effectively but also ensures fast and reliable operations, as hash map insertions and lookups are O(1) on average. Another way to solve this problem is by using a matrix representation of the display table. Here, the table is treated as a 2D matrix, where rows correspond to tables and columns correspond to food items. The matrix is populated directly based on the orders. While this approach may seem intuitive, it comes with significant drawbacks. First, the size of the matrix must be predetermined, which can be challenging if the exact number of unique tables and food items is not known up front. Additionally, the memory overhead is higher compared to using hash maps, as a matrix can become sparse, leaving many unused cells. For these reasons, the optimized approach using hash maps is a better fit for this problem. With hash maps, we can efficiently count food items per table and ensure correct ordering by sorting the unique food items and table numbers. This strategy strikes a balance between time and space efficiency, making it more scalable to handle the problem's constraints. Sorting does introduce some overhead, but given the manageable input sizes, this trade-off is acceptable. On the other hand, brute force and matrix-based approaches are less efficient and harder to implement at scale, which is why they are not ideal choices. The implementation of the chosen strategy involves a few clear steps. First, we parse the orders list and populate a dictionary of dictionaries to keep track of the food counts for each table. Next, we extract the unique food items and sort them lexicographically to define the column order. Similarly, we extract the table numbers and sort them numerically. With these sorted lists, we proceed to format the display table by iterating through the sorted tables and food items, filling in the counts from the dictionary. This ensures the display table is constructed in the correct format. In terms of complexity, the time requirement is O, n plus m log m plus k log k, which accounts for parsing the orders, sorting the food items and table numbers, and constructing the table. The space complexity is O, n plus m plus k, covering the storage of counts and the unique items. These complexity considerations demonstrate that this solution is efficient and scalable, making it well-suited for handling large datasets while maintaining clarity and precision in the implementation process. In this problem, we are tasked with creating a display table based on food orders in a restaurant. Each order includes the customer name, the table number, and the food item ordered. Our goal is to generate a table where rows represent table numbers in ascending order, and columns represent food items sorted lexicographically. The cells of the table will show the count of each food item ordered at each table. To achieve this, the first step is to parse the input and initialize the necessary data structures. We begin by extracting all unique food items and table numbers from the orders list. Using sets for this ensures that duplicates are automatically handled, and sorting them later will give us the desired lexicographical and numeric order. Next, we initialize a dictionary of dictionaries, which will allow us to efficiently track the count of each food item for every table. This setup ensures that we are organized and ready for the next phase of the algorithm. Now that we've initialized our data structures, the next step is to populate them with the actual data from the orders list. We loop through each order, extract the table number and food item, and update the counts in our dictionary of dictionaries. Here, the outer dictionary uses the table number as the key, and the nested dictionary uses the food item as the key. This structure lets us directly increment the count for the corresponding table and food item pair. Once we have populated the data, we turn our attention to preparing the header row of the table. The header row will start with the word table as its first column, followed by the food items sorted in lexicographical order. This ensures that the column order is consistent and easier to interpret. With the data structure and header row ready, we are set to organize the data into a fully constructed display table. The next step in the process is to construct the display table itself. We start by sorting the table numbers in ascending numeric order, which determines the order of the rows. For each table number, we create a row that begins with the table number converted to a string. Then, we append the count of each food item to the row, following the order of the food items in the header row. If a table did not order a particular food item, we default the count to 0. This ensures that every row is complete and all columns are accounted for. Finally, we combine the header row with all of the table rows to produce the final 2D list. This list represents the completed display table, which we return as the output. By following these steps, we ensure that the table is both accurate and easy to read. Let's take a moment to review the data structures used in this algorithm and understand why they are well suited for this task. First, we use a hash map, specifically a dictionary of dictionaries, to track food item counts for each table. This structure provides O1 access time for both table numbers and food items, making it very efficient for updates and lookups. Next, we use sets to collect unique food items and table numbers. Sets are ideal for this purpose because they automatically handle duplicates and allow for efficient sorting. Finally, we use a list to construct the final tabular representation of the results. Lists are a natural choice for storing the rows of the table, as they are easy to construct and return as a 2D array. These data structures together provide a balance of simplicity and efficiency, ensuring that the algorithm performs well even with large inputs. To conclude, let's analyze the time and space complexity of this solution. For time complexity, parsing the orders takes O(n), where n is the number of orders. Sorting the food items requires O(f*log f), where f is the number of unique food items, and sorting the table numbers takes O(t*log t), where t is the number of unique tables. Constructing the rows involves iterating over the tables and food items, which takes O(t*f). Combining these, the total time complexity is O(n plus f*log f plus t*log t plus t*f). For space complexity, we need O(f plus t) for storing the unique food items and table numbers, and O(t*f) for the dictionary of dictionaries. Thus, the total space complexity is O(t*f). Overall, the algorithm is optimized for scalability, efficiently handling both the input size and the display table construction process. To solve this problem, we start by importing the necessary libraries and defining our solution class. Inside the display table method, the first step is to collect all the unique food items from the orders. For this, we use a set called food_items. Additionally, we create a nested dictionary called table_orders using default dict. This will help us keep track of the count of each food item for every table. The nested structure allows us to easily manage the food counts for each table without initializing keys manually. Now, we iterate through the input orders, which is a list of lists. Each order contains 3 parts: the customer name, table number, and food item. We don't need the customer name for this problem, so we skip it. Instead, we focus on adding the food item to the food_items set and incrementing its count for the respective table in the table_orders dictionary. Once we have processed all the orders, we sort the food_items lexicographically to create the column headers for our display table. After that, we start preparing the table structure. We initialize a list called display_table and add the header row to it, which consists of the word table followed by the sorted list of food items. This will form the first row of our final result. Next, we focus on constructing the remaining rows of the display table. For this, we iterate through the table numbers in ascending order, which is achieved by sorting the keys of table_orders. For each table, we start by creating a new row where the first entry is the table number as a string. Then, for every food item in our sorted list of food_items, we check if that food item exists in the current table's dictionary. If it does, we append its count to the row. Otherwise, we append 0, indicating that the food item was not ordered at this table. Once the row is complete, we add it to the display_table. After processing all the tables, the display_table list contains the fully constructed output, with the header row followed by one row for each table, in ascending order of table numbers. Finally, we return this display_table as the result, which satisfies the problem requirements. Here, we start by importing the necessary packages, such as java.util, to handle collections and maps. The focus of this solution is to process the given list of orders and structure them into a display table. First, we define a set called food items to collect all the unique food items from the orders. This will help us later when we sort and display the food items lexicographically. Next, we create a tree map called table orders that maps each table number to another map, which tracks the count of each food item ordered at that table. The tree map ensures that the tables are stored and iterated in ascending order of their numbers. Then, we loop through each order in the input. For every order, we extract the table number and the food item, adding the food item to the food items set. The table number is parsed into an integer for easy manipulation, and we use the putifAbsent method to initialize the map for that table if it doesn't already exist. After that, we update the count of the specific food item for the current table using the getOrDefault method. Finally, once all orders are processed, we convert the food items set into a list and sorted lexicographically using collections.sort. This ensures the food items appear in alphabetical order for the final output. Now that we have the sorted list of food items and the table-wise food counts, we move on to constructing the display table. We start by creating an empty list called display table to store all rows of the table. The first row is the header row, which includes the column names. It begins with the string table followed by all the sorted food items. This header row is added to the display table. Next, we iterate through the sorted table numbers from the table orders map. For each table, we create a new row that starts with the table number as a string. Then, for each food item in the sorted list, we retrieve the count of that food item for the current table using the getOrDefault method, which provides a default value of 0 if the food item was not ordered at that table. These counts are converted to strings and added to the row. Once the row is fully populated, it is added to the display table. After processing all tables, the complete display table is returned as the result, providing a structured and sorted representation of food orders across all tables. To solve this problem, we start by understanding the input structure and setting up the necessary data structures. The orders list contains details about each order, including the customer's name, the table number, and the food item. Our goal is to organize this data into a display table that shows how many of each food item were ordered at each table. First, we initialize two key data structures, food_items, an empty set to collect all unique food names, and table_orders, a nested default dict to count how many of each food item were ordered at each table. For the first order, David, 3, ceviche, we add ceviche to the food_items set and update the count for table 3 in table_orders. This approach will allow us to systematically process all orders and build the required data for the final display table. Now, as we process each order in the input list, we update our data structures. For example, after adding the first order, food_items contains just ceviche, and table_orders tracks that table 3 has one order of ceviche. As we process the remaining orders, we continue to update these structures. By the end of processing, food_items contains all unique food items, ceviche, beef burrito, fried chicken, and water. The table_orders dictionary now maps each table number to a count of the food items ordered at that table. For instance, Table 3 has 2 orders of ceviche and 1 order of fried chicken, while Table 5 and Table 10 have their respective food orders. Next, we sort the food_items lexicographically, which gives us the order beef burrito, ceviche, fried chicken, and water. With this sorted order, we can now construct the display table. We start with the header row, which includes the column table followed by the sorted food items. Then, for each table, sorted numerically, we create a row that shows the table number and the counts for each food item. The final display table is ready, where each row corresponds to a table and its orders. The output for this example is a two-dimensional list where the first row is the header, and the subsequent rows represent the food orders for each table. The header includes table followed by the sorted food items, beef burrito, ceviche, fried chicken, and water. For table 3, the row shows 3, followed by the counts for each food item, 04 beef burrito, 24 ceviche, 14 fried chicken, and 04 water. Similarly, rows for tables 5 and 10 show the respective counts of food items ordered at those tables. This structured display table allows us to clearly see the food order breakdown across all tables in the restaurant. In this simpler example, there is only one table, and all orders are for the same food item, pasta. We follow the same steps as before. First, we initialize food_items as an empty set and table_orders as a nested default dict. As we process the orders, we add pasta to food_items and update the count for table 1 in table_orders. Since all orders are for pasta at table 1, food_items ends up with just one item, pasta, and table_orders shows that table 1 has 3 orders of pasta. After lexicographically sorting food_items, which remains as pasta, we construct the display table. The header row includes table and pasta, and the row for table 1 shows 1 followed by the count 3. The final display table provides a clear view of the single table's order. In this final example, the orders list is empty, meaning no orders were placed. We still initialize our data structures, food_items as an empty set and table_orders as a nested default dict, but since there are no orders to process, these remain empty. When we attempt to sort food_items, the result is an empty list, and there are no tables to process for the display table. Therefore, the header row of the display table contains only table, and there are no additional rows. The output is a simple table with just the header, which accurately reflects the absence of any food orders. To analyze the time complexity of our solution, let's break it down step by step. First, we process the orders by iterating through the orders list. Each order involves extracting the table number and food item, which takes constant time per operation. With n total orders, this step contributes O(n). Adding food items to a set for unique tracking and updating the nested dictionary of counts also operates in constant time per operation, so this step remains O(n) overall. Next, we sort the unique food items. Since the items are stored in a set, sorting them lexicographically takes k*log k, where k is the number of unique food items. After that, we sort the table numbers, which are extracted as keys from the table_orders dictionary. Assuming there are m distinct tables, this sorting step takes m*log m. Now, let's look at preparing the final display table. For each table, we iterate over all unique food items to construct a row. With m tables and k food items, this step contributes m*k. Adding up all these contributions, the total time complexity becomes O(n) for processing orders, k*log k for sorting food items, m*log m for sorting table numbers, and m*k for preparing rows. In the worst case, where the number of unique food items k is proportional to n, such as when all orders contain distinct food items, the sorting step dominates. This results in a worst-case time complexity of O(n*log n). Next, let's analyze space complexity. First, we store unique food items in a set, which requires k space, where k is the number of unique food items. Then, the table_orders nested dictionary stores counts for each table food combination. In the worst case, where there are n tables and k unique food items, this requires m*k space. Additionally, we maintain sorted lists for the unique food items and table numbers. These sorted lists require k and m space, respectively. Finally, the display table itself is a 2D list with dimensions, m+1 x, k+1, including headers. This also requires m*k space. Together, the dominant term in space complexity is m*k, as it represents the largest contribution. To summarize the overall space complexity, we add up the contributions, k for the food items set, m*k for the table_orders dictionary, k for the sorted food items, m for the sorted table numbers, and m*k for the final display table. The dominant term remains O, M asterisk K. Comparing this to a naive approach, where we process every order repeatedly for every table and food combination, we can see the advantage of our optimized solution. The naive approach would require O, N asterisk M asterisk K, time and less efficient space usage due to redundant storage. Our optimized approach, by leveraging sets and dictionaries, reduces the time complexity to O, N asterisk log N, while maintaining a space complexity of O, M asterisk K. This efficient handling of operations minimizes unnecessary computations. Finally, let's examine the best, average, and worst-case scenarios for our solution. In the best case, where all orders belong to the same table and involve very few unique food items, the time complexity is O, N plus K asterisk log K, and the space complexity is O, K. In the worst case, where every order involves a unique table and food item, the time complexity becomes O, N asterisk log N, and the space complexity is O, M asterisk K. The average case lies between these extremes, depending on the distribution of tables and food items. Overall, our optimized solution ensures efficient handling of the worst case while remaining practical in the average case, making it well suited for this problem. When solving this problem, there are several common mistakes to watch out for. First, many people forget to account for edge cases such as empty input lists, scenarios where there's only one table, or when there are duplicate orders. Overlooking these can lead to runtime errors or incorrect results. Another frequent mistake is using inefficient nested loops, which can result in time complexities like O, N squared, or worse. This approach becomes impractical for large datasets, especially when the problem constraints are high. It's also important to avoid hard-coding food items or table numbers. A solution that assumes a fixed set of inputs will fail for dynamic or unexpected inputs. Finally, sorting results incorrectly, like not sorting table numbers numerically or food items alphabetically, will cause your solution to fail test cases, as these are specific problem requirements. Additionally, directly modifying the input list while iterating through it is a common pitfall. This can lead to unexpected behavior or data loss, making debugging especially challenging. It's better to adhere to immutability principles. From an interview perspective, understanding the problem requirements is key. Pay close attention to details like ensuring tables are sorted numerically and food items are sorted lexicographically. Small oversights here can lead to incorrect solutions. For large inputs, focus on optimizing your approach. Avoid high-complexity solutions like O, N squared, by leveraging data structures such as dictionaries or hash maps for more efficient lookups and aggregations. Lastly, always test your solution against edge cases during implementation, like no orders being present, all orders coming from one table, or multiple orders for the same item. This ensures your solution is robust and handles real-world scenarios. When explaining your solution to an interviewer, it's important to be clear about the trade-offs involved. If you start with a brute force approach, acknowledge its limitations and outline your plan for optimizing it. This demonstrates both your problem-solving skills and your ability to think critically about efficiency. Related problems can also give you a broader perspective. For example, LeetCode 49, which focuses on grouping and sorting dynamic data, shares some conceptual similarities. LeetCode 692 and 347 both involve frequency counting and sorting challenges, with 692 focusing on strings and 347 on general elements. Additionally, LeetCode 451 emphasizes frequency counting and arranging data in a specific order. Reviewing these problems can help reinforce the techniques needed to solve this one effectively. There are also alternative approaches worth considering. Using a hash map to store table food counts is a common method. After processing, you can sort the tables numerically and the food items lexicographically. This approach is efficient, with a typical time complexity of O, N log N, though it does involve additional sorting steps. Another option is to represent the data as a matrix, where rows correspond to tables, and columns represent food items, with counts populated dynamically. While this can simplify the logic, it may increase space usage significantly if the number of unique food items is large. Pre-sorting the input data by table and food is another strategy. This pre-processing step can make the aggregation logic simpler, although it does add some upfront computational cost. Weighing these trade-offs can help you select the approach that best fits the problem constraints and requirements. Great job following along. Today, we tackled the problem of displaying a table of food orders in an efficient and organized way. Remember the key techniques and concepts we covered, they'll be invaluable in interviews and real-world scenarios. Thanks for watching, and stay tuned for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!